Okay, on this worksheet we're going to look at what a Cauchy-Euler ODE is. We're going to look at the determinant operator, and we'll look at solving a system of first-order differential equations. So let's start with a definition for a Cauchy-Euler differential equation. A Cauchy-Euler ODE is in the form shown. The important part for a Cauchy-Euler ODE is that you've got this x to the nth power multiplied by the nth derivative. You have an x squared multiplied by the second derivative. You have an x multiplied by the first derivative, and then there are no x's multiplied by your y. Of course, your differential equation may be homogeneous or non-homogeneous, depending upon what the function of g of x is. There are two ways that you could solve Cauchy-Euler ODEs. One way is by converting it to a linear ODE with constant coefficients by making the substitution x equals e to the t. Now, when you make that substitution, the actual derivative, finding the derivative, is probably the hardest part, not substituting in. Let me see where my mouse is. Whoops. So here on number 1, if x is e to the t, let's find dy dx, and then let's find our second derivative with respect to x. So I'll start with my first derivative. There's my mouse. And in order to get dy dx, I'll have to use the chain rule. Dy dx is dy dt times dt dx, because x is defined in terms of t. So here I have x defined in terms of t, and what I'm really looking for here is my dt dx. That should be a dx. I need the derivative of this with respect to x. Let me take this equation, x equals e to the t, and solve it for t. You can solve for t by taking the natural log of both sides. And then on the right side, the natural log and the exponential drops out, so that you get t is equal to natural log of x. And now I can take the derivative of t with respect to x. And on the right side, taking the derivative with respect to x is going to give me 1 over x. Okay, so if I substitute in here, I get dy dx is equal to dy dt times dt dx is 1 over x. When I take the second derivative of y with respect to x, then I'm applying the derivative with respect to x of this right side. And here I'm applying the product rule. So I want the derivative with respect to x of dy dt times 1 over x plus the derivative with respect to x of 1 over x times dy dt. When I do this first derivative, I'm going to do the chain rule, where dy dt is dy dx times dx dt. And then on this second term, here I can just take the derivative of 1 over x with respect to x. That's the same as the derivative of x to the negative first, which would be negative 1 x to the negative second, or minus 1 over x squared dy dt. So here in this first parenthesis, what I'll do is I'll substitute in. I know that dx dt is 1 over x. I know that dy dx is dy dt times 1 over x. Let me put that here. And actually, let me keep this as dx dt. So that I can cancel these dx's. And notice that I get the derivative of y squared, d squared y over dt squared with respect to t squared, times, here I have 1 over x times 1 over x, that's 1 over x squared, minus 1 over x squared dy, and that should be a dt, not a dx. dt, that's from here, dt. dy dt, and if you want to, you could factor out that 1 over x squared, and you get the second derivative of y with respect to t squared minus the first derivative of y with respect to t. So here taking the derivatives takes a little bit of time, but if you use these substitutions into a Cauchy-Euler ODE, then you can convert the Cauchy-Euler ODE into a linear higher order ODE with constant coefficients, and it may make the work a little bit easier. So we're going to look at two problems, and we'll do one using this method with these substitutions, and then we'll do the other one using the other method. And you can choose whichever method you want to choose when you're solving a Cauchy-Euler ODE.